Welcome everybody to another installment of our Science by Diverse Scientists seminar series. So today we're very pleased to have Professor Luz J. Martinez-Miranda speak with us. And she's a professor in the Department of Materials Science and Engineering at the University of Maryland, College Park. So a little bit on her background. So she received a bachelor's and master's in physics from the Universidad de Puerto Rico in Rio Piedras, and then went to MIT for a PhD. She'd also gotten a bachelor's in music, actually, at the Conservatorio de Música in Puerto Rico. Her research focuses on liquid crystals, which she's going to be discussing with us here today. She's been teaching a course on liquid crystals and also a visiting professor at the Liquid Crystal Institute at Kent State University and various other places. She has been serving on various committees, including being on the board of the International Liquid Crystal Society and is a member of their diversity committee. And she's additionally been involved as president of the National Society of Hispanic Physicists, and served on the Committee on the Status of Women in Physics and Committee on Minorities for the American Physical Society, and been on the board for the Society for the Advancement of Chicanos and Native Americans in Science, or SACNA, whose conference is going on right now, which is why I'm wearing my t-shirt from this. She has also received various prestigious awards, like being a fellow of the AAAS, American Association for the Advancement of Science, and is a winner of the Edward Boucher Prize from the APS. So we're very pleased, to have Professor Martinez-Miranda to speak to us today. The floor is yours.
Thank you. I thank the Calbridge program for inviting me to talk about the properties of a nanocomposite consisting of a mixture of a liquid crystal and a magnetic nanoparticle and their possible use in MRI. I actually took the liberty of copying the Calbridge symbol to remind me that when I was at Berkeley, I used to look out of my office window and see the Golden Gate Bridge, even when it was covered with fog. And I used to love that. So before we start, we at the University of Maryland at College Park believe it is important to create dialogue to honor those that have been historically and systematically disenfranchised. So we acknowledge the truth that is often buried. We are on the ancestral lands of the Piscataway people, who were among the first in the Western Hemisphere. We are on indigenous land that was stolen from the Piscataway people by European colonists. We pay respects to Piscataway elders and ancestors. Please take a moment to consider the many legacies of violence, displacement, migration, and settlement that bring us together here today. And the next thing I'm going to talk to you is the Calbridge people asked me to tell the attendants, how did I become a physicist? I was very, very lucky that I had a group of people that backed me up. The first person was my maternal grandmother. She only had a third grade education. She loved school and she loved learning, but those were different times and she was needed by her parents and her older sisters to go work in the land where they were working. So she couldn't go beyond the third grade, but her love of learning and her love of education translated into her children, my mother and my uncle, to the point that when my mother was about to graduate from 8th grade, and my uncle was also about to graduate from high school, her friends told her, why don't you pull those children off school and put them to work? And that way you will be in a more secure financial condition. This was because this happened just after the Great Depression finished and the Second World War started. And it was not a good financial situation for anybody, especially in Puerto Rico. And she said, as long as I can work, the children will stay in school. And if they want to go to the university, they will go to the university. And so it was. So my mother went to the university and got her degree in chemistry. And then went to work as a chemist and met my father, who was another chemist. So I had my grandmother that was a great influence in my mother, and it translated into me and my cousins and my brother, and my parents. And my two parents were scientists. So there was no difference that, oh, you're a girl, you cannot do science, because my mother was a girl and she did science. So I did not feel stopped from wanting to go into science. However, I was looking into being a chemist. And the story goes that my father never did forgive me that I went into physics. And who turned me to physics was my high school teacher, Don Leonardo Morales, who instead of starting with the vector algebra, the way that the regular physics courses started at that time, he started with optics. And optics was a very visual and a very visually appealing thing. And I think that visually appealing things appeal to me. So that actually turned my attention to physics. And the fact that I had all these people behind me helped me to know that I could do whatever I wanted. And this was introduced by David. So I will only say that my advisor for the MS at the Universidad de Puerto Rico was Dr. Fernando Diaz Colon, and my advisor for the PhD at MIT was Dr. Robert J. Virginal, and he is now in Berkeley. Then I got my bachelor's in music. And the greatest lesson I still bring from Puerto Rico is that what you need is your brains principally to do your work, because Puerto Rico was not known as a place that had any good equipment or any lots of money at the time that I was a student. Afterwards, they got some money, they got equipment, but what we had was our brains. And what I want to tell the people, especially the students that are hearing me now, is to count on your brains first, and then count your equipment and your money as a blessing. Because it is your brains that advance the physics. It is not the equipment or the money. So at the end of my, when I got my PhD, Dr. Virginal actually told me to run as far away from what he did as I possibly could. I did not appreciate this, because he didn't tell this to any of his male students. Afterwards, I understood that me being a woman and myself being also a minority woman, the people always looked at a person that was working on some aspects of their thesis as being still working for their advisor. And it was much more for a woman than for a man. I hope that this has changed. I haven't looked at it to see if it has changed, but that was how it was at that time. But the problem was, he introduced me to liquid crystals, and liquid crystal is a very visual field. So that's what attracted me to liquid crystals. And liquid crystals are described by de Gennes novel laureates as being beautiful and mysterious. So it was very difficult to take me away from liquid crystals. So I decided to go the more applied route, since my advisor followed a more basic one. And my postdoc at the University of California, Berkeley, helped me on that path. I have to confess that several times I tried to do other things, but always return to the liquid crystals. As they love to say in those stories, you always return to your first love. Well, liquid crystals is not my first love, but it's as close as possible to the first love. So before I finish this part, I will tell you what I love about being a physicist. In my field of study, in my chosen field of study, the interdisciplinary nature of my work is something that I love the most, because I get to talk to mathematicians, to biologists, to chemists, to engineers, to pure engineers, not like me. I'm a fake engineer. This allowed me to move into a material science, which, like my dean tells, oh, you're too basic. You almost do not belong in engineering, but it belongs in engineering. I love the other thing is meeting with people from all over the world and getting to discuss not only our work, but what we like to do. And amongst other things, I love to travel, which means I'm kind of frustrated with the pandemic. And at home, I love to show other researchers and my results as part of a class, because this activity allows me to reach to the students, not only my students, but the students in general, and helps me to teach the students that they are not learning in the class things that they might not use. They are learning things that they will use. And by showing them the work of other researchers, especially, I am showing how they apply that. So with that, I will give you the outline of my talk. And my talk consists of what is known that inspired us in the choice of materials that we were going to use. I will review, this will be a quick review for those of you who know about liquid crystals, but I want to put everybody in the same space. And then I want to look at what does a liquid crystal do to or with a liquid crystal? I mean, what does an electric field do to or with a liquid crystal? What does the alignment of the liquid crystals do to the magnetic nanoparticles? What is a ferroic system? Or more specifically, what is a multiferroic system? I will show you some previous work that helped me in this work. Our system, some results, and in between, interspersed with the results, I will talk about things that I would like to do as a future work. Before I go on, I would like to recognize my collaborators that come as far away as the University of Chile in Santiago, Chile. And I've had a collaboration that has lasted several years, and I was able to go there for my sabbatical. And they are experts in ferroelectric liquid crystals and in polymeric liquid crystals. So they helped me a lot in this project. And the people from Weinberg Medical Physics, this is a startup company located in North Bethesda, who were the people that came to me and asked me, is this possible to do with liquid crystals? And my UMD affiliate, who is my collaborator for more than 15 years. I would like to recognize the funding that made it possible for me to go and spend my sabbatical. So what is known? The nerves in the body, in our body, send electrical signals, but these electrical signals are very weak And what they wanted to do at Weinberg was be able to read this electrical signal and translate it into a magnetic signal that could be read by the MRI, so that they could get some information about things that happen to the body. So this has some questions. So what they wanted to know was, is there a mixture of liquid crystals and magnetic nanoparticles where the liquid crystal will be aligned by the electric field, and this alignment will create a magnetic field through the magnetic nanoparticle. What I have described up here is a ferroic system, or part of a multiferroic system, but I want to stay in this question. Is there a mixture of liquid crystals and nanoparticles where the liquid crystal can be aligned by an electric field and in turn will produce a magnetic field? And the short answer is yes, because Dr. Baer, who was one of the people from Weinberg, came to me at the University of Maryland, and we tried asbestic A, this is the HCB, mixed with nanoparticles, and we applied an electric field and looked at how it was organized by the electric field. And then what he did is he went back to Weinberg Medical Physics, to the lab that they have there, and he tried it also in his system, which actually where he mixed the system with nanorods. And what he found was a 5% increase in the MRI signal over the null voltage when electric fields of 20 volts per meter and currents of 12 nanoamps are applied to the contrast agents. This is shown in I and double I over here. So you say that you finished the work. So what is the problem? Well, it had a little bit of problems because we needed too large a concentration of nanoparticles, 30 to 50% weight for the asbestic A. And even though these were performed with nanorods, the concentration was still too high. And remember that we are wanting to apply this into a bio application. So you do not want as high a concentration of nanoparticles or nanorods. So that sent us into looking for a liquid crystal, for a liquid crystal that would be. But then people will ask me, what is a liquid crystal? And I am utilizing this because some talks that we had with students in the University of Maryland actually impressed them there. They're everywhere. They're in your phones, in your TVs, if they say that they are liquid crystal TVs, in the computers, which are so necessary nowadays, especially. They're used in photovoltaic applications and other organic electronic devices, and more principally, they're used by Mother Nature in life. We would be blobs of water if it were not for the liquid crystal phases. The liquid crystals that sustain life are mostly what is known as lyotropics. Those are liquid crystals that change their phases as a function of the concentration of a solute, in addition to actually changing phases when you change the temperature. And they are the molecules that constitute the walls of the cells. That's why we are not blobs of water. The DNA, the constituents of proteins, and so on and so forth. But what is a liquid crystal? Well, the liquid crystals that I'm concerned about are the Thermotropics liquid crystals that change phases with a change in temperature. So going away from the liquid crystals in life that actually have everybody all excited, I'm going to look in the thermotropics, and within the thermotropics, we have a whole range of shapes of liquid crystals, but I am only interested in these elongated molecules. And the elongated molecules, for anybody that does not have a chemist at the end of his or her or their degree, are designated like these ellipsoidal shapes. So for these presentations, liquid crystals consists of a long molecule with long carbon chains. You cannot have short carbon chains because you won't have a liquid crystal. And a core that consists of ring structures, and they have to be at least 2 ring structures. The ring structures are responsible for aligning the molecules on top of each other or side by side, and the carbon chains are responsible for the faces that the liquid crystal has. And I put this succession of temperatures to show you that the liquid crystal has 2 faces. So in our example, we have 2 liquid crystal faces. So the first one is a smectic A phase, which is a layered phase. And a layered phase looks like a bookshelf that is full of books and allows the molecules, these elongated ellipsoids, to, on the average, stand at 90 degrees with the layers that separate them. The second phase that they have is a smectic C-star shape. But for the time being, let me concentrate only on the smectic C. The smectic C is a layered phase, such as the smectic A shape. But the molecules in this case are not at an angle that is at 90 degrees. They're at an angle that is smaller than 90 degrees. And why do they get this smectic C shape? This is a vector that is produced by this substituent for the hydrogen in the carbon chain. And this substituent in particular is fluoride. Fluoride is the most electronegative of the elements in the periodic table. And what does that mean? That fluoride attracts the charge density up towards the fluoride. So it leaves an effective positive charge near the chain, and the negative charge is concentrated in the fluoride. So you have positive and negative, they form a vector. And this vector is known as a polarization vector, or as a spontaneous polarization vector. The fluoride is also known as a chiral component. And the last thing I will say about the phases is that if you look again at the temperature construction, the phases of the liquid crystal appear or happen between the solid and the liquid phase of a material. So what does an electric field do with or to the liquid crystal? So let's take the smectic A phase. So if we have a liquid crystal that does not have a chiral group, the electric field will tend to align the long axis with it. And in aligning the long axis with it, it will separate the charges along the long axis. And because of this, because it has to one, separate the charges along the long axis, and it aligns the long axis, this requires a relatively large field. How large? Again, I cite what we did, what we tried in the lab. So this is our smectic A liquid crystals, and I have a let's say a X-ray scattering experiment that has the incoming beam on this direction and the outgoing beam in this direction. And when they are in in this type of orientation, you can only see the short axis of the molecule. You don't see the long axis of the molecule until they couple with the electric field. And how high is the electric field that you need? Well, here is some results with, again, the ACV molecules. You need a field of at least 50 volts per centimeters. That's 50,000 volts per meter. So it's too high a field. So now let's ask the same question with a ferroelectric liquid crystal that has this spontaneous polarization. And the spontaneous polarization, remember, I said that it separates the positive charge from the negative charge. So it already has a separation, so the electric field doesn't need to look for it. So the electric field will couple to the spontaneous polarization and then turn the liquid crystals on their small axis. And because it's turning on their small axis and the liquid crystal has the polarization, it needs a lower electric field. Now, assume that we have aligned the liquid crystals. What does the alignment of the liquid crystals do to the magnetic nanoparticles? So we have the liquid crystal with its spontaneous polarization, and we have a nanoparticle that will have a magnetization associated with it. And while you have a quote unquote disordered phase, the magnetization will be pointing in every one direction. That means that the magnetization will not be adding or subtracting itself. But when you apply an electric field, the liquid crystal molecules were ordered. And then that actually pushes the magnetization or the nanoparticles to places where the liquid crystal has a dislocation or defect, or to the spaces in between the layers. And then the magnetization will actually feel the magnetization of its neighbors or its next to its neighbors, and will, on average, align itself into one direction. And this will result in a magnetic field. So this is the description of a ferroelectric system. A multiferroelectric system has an electric field producing a magnetic field, or an electric field producing some distortion in the elastic field. Or the distortion can actually produce an electric field or a magnetic field, or this three. This has been known in solid state materials for many years, but in liquid crystals, the study started circa 2010. I say circa because that is the earliest references that I could locate. So that means that the previous results were not on ferroelectric systems. So the previous results that I wanted to look at dated back to 1996. It showed how a nanomagnetic particle could decrease the magnetic field needed to align a liquid crystal. Now, there are some that date back several years, but they deal with a nematic liquid crystal. A nematic liquid crystal is a liquid crystal that does not have layers, but the molecules are pointing in the same direction. That means that it is it's kind of like a disordered version of a liquid crystal. As I said, the systems were not ferroic because the studies began to be circa 2010 on liquid crystals. And what distinguished my studies of the nanoparticles on liquid crystals with these previous studies, it's first that the previous studies dealt with with nematics, or with some of the lyotropic systems. And I dealt with the effects of the magnetic nanoparticle and its functionalization compound on the orientation of the smectic A liquid crystals. And why did I use the smectic A liquid crystals? Well, it turns out that the smectic A liquid crystal needs a magnetic field of about 4 Tesla to orient it. And we needed the ordered phase for our particular work. This work, these are 2 of the papers. There's about 3 or 4 more, but they are minor papers. And they are needed, and the ordered liquid crystal is needed for this work. So I show you the results, the basic results that came out from this work, where you see in the y-axis the functionalization compound, and on the x-axis the size of the nanoparticle that we were looking. And I'm sorry, this should be 11 nanometers. And you see that at every point, if you apply a field, the order of the liquid crystals will actually change. But this field is very small. It's 362 millitesla, not 4 Tesla. So we actually were able to change the order or disorder the liquid crystal more with just a small magnetic field. So now that brings us to what we used. So we suggested to use a ferroelectric liquid crystal for the reasons that were made obvious in the consideration of the electric field, because they would decrease the electric field needed. And the second reason is because we hoped to decrease the nanoparticle concentration. And we used the same liquid crystal that I used to illustrate what was a liquid crystal as our ferroelectric liquid crystal. And we mixed it with nanoparticles of iron cobalt, which were in between 2.5 and 3.5 nanometers in diameters. And what is important of this size? Well, it turns out that the size of this molecule is between 3.2 and 3.6 nanometers. And if you want to mix 2 different compounds, it's better to mix 2 different compounds that have the same size, rather than have one that has a big, say, a big diameter for the nanomaterials. And then also take into consideration that this is an organic material. This is an inorganic material. So that's why we have the nanoparticles and their functionalization compound, because the functionalization compound is based on an organic material, and it actually ensures that they will stay mixed for a longer time. And how did we ensure that the iron cobalt particles were 2.5 and 3.5 in diameter? So we looked at them using X-ray scattering and using dynamic light scattering, and my collaborator had used also some TEM, which unfortunately I don't have. And they all agreed. Well, you might say, well, it doesn't look like this agrees that much with the X-ray scattering. Well, no, it's just that the dynamic light scattering, there is some signal that comes also from the functionalization compound. Then we needed to look at the ferroelectric results. We needed to look at the spontaneous polarization to make sure at what point the ferroelectric phase started as you change the concentration of nanoparticles in the ferroelectric liquid crystal, because we wanted to be at a temperature or at temperatures that were in the ferroelectric phase. In addition, we measured what is known as the rise time, which is a measure of how much it takes for the electric field to turn the liquid crystals and align them. And what we observed was that for certain concentrations, like the 0.53 and the 10.8%, the nanoparticles seem to act as a lubricant to the liquid crystal. And this is very important. Why? Because this rise time is proportional to the viscosity of the material. The viscosity actually acts as a resistance for the electric field to actually turn the material. So if it's acting as a lubricant to the liquid crystal, then it reduces the viscosity or reduces the resistance. So here we had the 0.53 was almost like having the 0%, but the 10.8 was almost perfect for it. So we decided to go to the 10.8% weight of nanoparticles in the liquid crystal. But the 10.8% weight of nanoparticles is a fairly high concentration. It's fairly low because it's lower than 30 to 50% weight, but it is high for the liquid crystals, which means that they at one point they will phase separate. So we wanted to see how they looked examined by the polarized microscope. And here we have we had taken some pictures with the smectic A, and because it has a lower transition into the isotopic phase, we were able to access it fairly easily with the equipment that we have in the microscope. And here you have the nanoparticles have come together and constituted themselves into what I will call a nano-cluster. And this nano-cluster, as you go from the isotropic to the nanomatic to the smectic A, congregate themselves inside these droplets that form in the smectic A. Now you say, well, and did you go back and did the nano-clusters grow? No, we went back and the nano-cluster stayed the same size, and we were able to go back and forth, let's say in the smectic A. We also were able to observe the same effect in the ferroelectric liquid crystals, and by locating the nanoclusters inside the droplets of the liquid crystals. And we also observed that the droplets even existed at the 0% weight sample. What does that mean? That the droplets are marked the spaces where the liquid crystal is disordered from whatever phase it's supposed to be. And we were not the first persons to discover this, and it does not exist only in the smectic A or the ferroelectric liquid crystals or in this projection. It does exist. It has been observed in the smectics, and I mean in the nematics, and I point to you to two references, and I think these references are from UC Merced. So we decided on the 10.8% weight. So we then decided to look at it by changing the electric field. So we started with fairly low electric fields. Actually, we started with 5 volts per centimeter. And we observed that we had more of these droplets as the electric field increased. And as the electric field increased to the maximum electric field that we had, we observed that the droplets then now grew not parallel to the electric field, but they grew perpendicular to the electric field. Now, this was not of interest for our biological application, but was of interest to see what was the change. So the other thing with these droplets, since the droplets will contain the magnetic nanoclusters, we could make an estimate of how much those nanoclusters would contribute to the general magnetic field. And the contribution was 7 times 10 to the 3 Gauss, or 0.7 Tesla. And what is the significance of this? Well, it's a good thing, because Dr. Mayer told me that 0.7 Tesla is about what the MRI needs to be able to read a change. So we had arrived at the result that we needed. And we had arrived also at this result that was kind of a measure, an indirect measurement of how the magnetic field was changing, because unfortunately we had too small a sample for the available magnetometer or the MRI. And this is something that happens more often than you hear people admit, but I'm the first to admit. So we had gotten up to this point and published our results in liquid crystals for anybody that's interested. But I was still interested in looking at what happened to the droplets as the electric field increased. And I hope I can get this to work. If not, I will let it stay. I want you to look at this particular droplet. And if you see, it changed. And so there's some other droplets that changed in the liquid crystal. But since we don't have much time, we are only going to be to concentrate in this droplet. So this droplet changed from this this configuration to this configuration. And if you see, there are some magnetic nanoparticles that are kind of free of the droplets, and they tend towards the top of the of this droplet as the electric field increases. And so does the magnetic nanoparticles in this droplet. But let's concentrate in this and the changes that we observe in this droplet. So why do we study the other order or the ordering inside the droplet? And I should say that I'm not the first. There has been work that dates back to the 1990s, early 1990s, of people that have studied how the liquid crystals are aligned inside the droplets. And then we are interested in how the alignment of the liquid crystal influences the alignment of the nanoclusters. This has less references than others, but still has references. And what I want to do is to say something about the alignment of the magnetic moment inside the clusters. This does not have many people working on it. And this is work for the future. So we needed to find out how the nanoclusters change as a function of the liquid crystals changing their ordering as a function of an electric field. We needed to know where the clusters were located inside the droplets. And what I didn't say was that the picture that I showed, the two pictures that I showed for the ferroelectric liquid crystals were pictures that were shown at different depths of the field, of the film, of the portion of the film that we were studying. So I show them at the right height. This is the level where you can see the droplets, and then you can see most of the nano-clusters are below the droplets, but still inside the droplets. If you go and close by, and you can see still like the droplets surrounding it. So the nano-clusters are located at the bottom of the droplets, and you can think of it in simple ways, thinking about the gravitational forces. So the droplets are at the bottom of the droplet. The nano-clusters are at the bottom of the nano-droplets. So the next thing that we need to know is, how are the liquid crystals ordered in the droplets? We know that the liquid crystals are lying perpendicular to the surface of the droplet. So this means that if there is any phase that the liquid crystal might have, it may be the smectic A liquid crystal, just because the size of the droplet does not allow them to turn around and have and be at an angle. And at the center of the droplet, the liquid crystal is pointing every which way, so this center is a disordered center. The functionalization of the nanoparticles align the liquid crystals perpendicular to the nanoparticles. This was something that we got from our previous results. And then the other thing was that this nanodroplet doesn't look like this nice circular theme, but it looks like a fat ellipsoid. So why does it have the shape of an ellipsoid? It turns out that the ellipsoidal shape of the droplet is due to the rod-like shape of the liquid crystals. And now in my field of view, I can see the nanocluster just below, or just at the center, or interacting with this disordered center. That's why I put it in this blue circle that looks like a ring, but it's not a ring. It happens to be below the disordered droplet. So let's take a look at two other takes in the liquid crystal that I cannot see because I'm using a polarizing microscope that only allows me to see the CY phases. But if you look at the CX phases, you will see that you can have a situation where you get the nanocluster that is kind of like partly in the disordered phase, where only the first group of liquid crystals will try to order perpendicular to the faces. But then if it sticks to the order phases, then this order phases will actually, the molecules in the order phases will actually try to turn in so that the molecules are perpendicular to the surface of this droplet. When they turn in, they will create a defect line, a dislocation line, and then that will look like this. And this actually designates the surface, the center of the droplet, and these are the dislocation lines of the liquid crystals as they turn into the nanocluster. And this is the structure that you observe. And I did not do this just because I was looking at this. I was using certain references out of which I put 2 here. Okay, what happens when I applied an electric field? And I apologize because this is the XY projection. This is the CX projection. And this is the CY projection, the projection that I'm looking at. So in the XY projection, I don't see that much. But in the CY projection, I can see what happens when you have the nanocluster. And remember that I told you that the liquid crystal inside that droplet was in the smectic A. So this line is a line of molecules that tend to organize themselves parallel to the electric field, except when they encounter that nanocluster. So then they will organize themselves such that they align perpendicular to the nanocluster, and they adopt this defect structure that is known as a Saturn ring. And you can see the Saturn ring here. And this is a reference that discusses the Saturn rings. What happens when you increase this electric field? I remember that as I increase the electric field, the droplets would actually start showing up perpendicular to the direction of the electric field and very close together. So what I think happens, and this is just hand waving myself, is that as the electric field is increased, the center of the sample wants to be as aligned with the electric field as possible. So since this cluster is not a solid material, it's a collection of nanoparticles, can break up and concentrate on the most disordered part of the droplet. So you have the liquid crystal ordered in the direction of the electric field, and then you have these 2, let's say, cluster portions that then associate themselves to the clusters of the next droplet, just as shown here. But this is hand wavy, and I'm at the point where I want to summarize. I showed you that we studied the effects of ferroelectric liquid crystals on clusters of magnetic nanoparticles and found out that we can order the magnetic nanoparticles at low electric fields by having the magnetization at increasing the magnetic field. This was the first part of my talk. The second part was, as the electric field increased, we observed a change in the droplets that resulted in further alignment of the clusters. And I'm asking myself, what does that do to the magnetic field? Does it result in a further realignment? Does it result in a change in the orientation of the magnetic field? So that is some of the work that I would hope to do if I got some money. But at this point, I finished my talk and I open the computer for questions.
Thank you, Professor Martinez-Miranda, for a wonderful talk. Very wide-ranging, very applied and fundamental. So we have one question currently typed in the chat, and that's from Alana Wheeler.
Okay.
Hello.
Oh, glad that she was able to make it.
Yeah. So I'm not able to unmute her. I don't know if she's able to unmute herself. Fellow panelists, can you help me out?
I cannot. Oh.
There we go. She can talk now. She can unmute herself now.
Thank you. Go ahead, Alana.
So you had the paper, or no, the information where you were talking about that the liquid crystals are aligned perpendicular to the surface of the droplets. And I was just wondering if you have a reference that I could go look that up. That's actually information I've been looking for.
I don't know if the paper that I cite there has, but let me look at it and let's see if I can. If you can send me an email with your address, so I can send you the reference.
All right, I can do that. Absolutely.
Okay, and
Thank you.
And do you know my email?
I thought it's probably on, you know, maybe I don't.
I'll get you in touch, don't worry.
Okay, thank you.
Okay, yes. Yes, because I'm not sure if those references are the references that I gave, because there were many references. So I had to choose, because if not, I would have to talk full of the references that would take like an hour to go through, and then an hour else to go through the work. That is not practical.
Oh, thank you. I'll send an email for sure.
Okay. You will probably get the answer by tomorrow, because remember, it's almost 8 o'clock my time.
Well, yeah, don't worry. The baby it'll keep me busy for the rest of the day, so I won't be able to see a response till tomorrow anyway.
Okay. I have to confess, I can't see anybody. And I'm afraid of stopping the sharing. Oh, now I can see everybody.
Great. So any other questions from students in the audience? Here's one from Eric Santos. Let's unmute him.
Okay.
Yeah, sorry, I'm not in this field, so I'm trying to wrap my mind around it, but I was just wondering if you could sort of summarize what your practical applications of the work are?
Oh, the practical applications were to use the liquid crystal, the system consisting of the liquid crystals and the magnetic nanoparticles as an MRI detector or translator. So they would take the electric field from the nerves of our system, translate it into a magnetic signal that would be detected with the MRI. There were some practical problems with this that the founder of Weinberg Medical had already worked into some of the how would I say, the little needles that he was planning to put very close to the nerves, and he couldn't see how we could put the liquid crystal magnetic nanoparticles, but they still read low electric fields and translate into the high magnetic fields. So if he so chose, he could modify the geometry of the needles that he wanted to put. And he was not experimenting with human beings. He was experimenting with horses.
Thank you.
So I was wondering if you could tell us a little more about how that collaboration started with the MRI researchers or inventors.
Well, it turns out that I have a student of mine from many years ago that is also works in Maryland, and she knew the people from Weinberg through some other type of work, and they were looking for a person that knew more about liquid crystals. Now, when she worked with me, she worked with liquid crystals, but she has moved away from that. So she said, no, but I know a person. So she put us in contact with each other.
So it was their idea to seek someone in the liquid crystals field?
Yes.
Wow, okay.
Yes, and as I said, I think she also presented them with our previous results that actually pointed out that there was some hope in achieving what they wanted to achieve.
Any other questions? Okay, if not, let's thank Professor Martinez-Miranda again for a wonderful talk.
Thank you very much, and thank you for having me.
Thank you so much.